Hi, welcome to my channel, JaberTime. Today I'm going to go over line integrals in space, which is very useful for the coming sections, all of them. Let's get into it. I have some formulas on the front slide, but there is more on the coming sections for line integrals. Here we go. Line integrals. In a single variable, we start by partitioning the length or the arc into pieces. From this point to this point, x sub 0, y sub 0, x sub 1, y sub 1. This will be called the hypotenuse, which is S1. Doing the adjacent and the hypotenuse, finding the adjacent and opposite, and finding the hypotenuse, which is S1, or using the distance formula, we end up with the following. That's my A, delta x, for the first one. That's delta y, that's my B. A square plus B square, under the square root will give you C, or differently, we just call it the distance formula. We do the same thing for the other parts, S2 and on. To reduce the work here, because this is just an introduction, we need the sum. To enhance this, I could, inside the square root, factor out delta xi square. Once you do that, this becomes 1, and this becomes, to adjust it back, I need a delta xi square in the denominator. Let's apply the square root to both parts or factors, and this now becomes delta xi. Now this is a nice form for integration. After you apply the limit, becomes integration, and that's the final answer. So the length of the arc in a single variable calculus, we have the following: 1 plus f prime to the second under the square root dx. Arc length. It's good to connect single variable to multivariable because the formulas are about the same. You're going to see 1 plus, but you're going to see it with more variables coming. So let's move on. Instead of integrating over an interval from A to B, we integrate over a curve C. And that's called line integrals. So instead of flat from A to B as x, we are actually tracing the curve from point A to point B. We start with a plane curve C given by the parametric equations. X equals x of t, y equals y of t, and t goes from A to B. Or equivalent by the vector equations, writing it as a vector, x of t I plus y of t j. Now, this is the line integral. Instead of f of xy, we're going to write it in terms of x of t of and y of t, and ds is this right here, which kind of like relates to the first slide that I showed you earlier. Now, if you want the arc length, f would be 1. So if you have a function f xy in your way, that's not an arc length. That's called line integral. But if you want the length only, that should be 1 right there. Okay, which is just like you're integrating this part, which is called ds. Just keep that in mind. So, if s of t is the length of c between r of a and r of b, that should be b, then ds dt, that's also from the first slide, almost. So ds, keeping it by itself, will be the square root dt. You're going to see this a lot on the coming sections and the integration. Here's an example. Evaluate the line integral 2 plus x squared y ds, where c is the upper half of the unit circle described right here on the top half, as you could see. Using parametric equations, we're going to write x as cosine t, we're going to write y as sine t, we're going to go from 0 to pi, for the angle or for t. I'm using colors right here. I'm highlighting my notes because the main focus is not when I speed up reading those or calculating. The main part is knowing how to start, how to finish. So this is my ds in red. This is my function. Instead of calling it C, I'm going to go from A to B. So we're going to change the language to T. This is the problem right here. We're going to change X to cosine, and we're going to change Y to sine, as you could see. Now this right here is dx dt square, dy dt square, which is cosine square minus sine square and cosine square, but it's going to end up with a positive because you're going to square it. And this whole thing becomes 1. And that's one of the benefits about polar forms. It changes from using square roots as your limitations to completely different limits and simplifies your calculations. So with that in mind, use u substitution. Cosine, the derivative is minus sine. That's why I chose a minus sign. U squared becomes u cubed over 3. I'm going a little bit fast right here because I do have it anyway for you, so you could slow me down or stop the video by hitting the space bar, read it, confirm, and move on. But the main part is how do you start and how to use the formula. Doing the math, I got 2 pi plus 2/3. Okay, that should do it for this example. Let's take another one. In case you need the line integral, but C consists of C1, which is the parabola y equals x to the second from 0, 0 to 1, 1, and followed by the vertical line segment from 1, 1 to 1, 2. I'm using blue for this portion. I'm using green for the second part, C2. So I'm going to stay focused with C1 first, then we'll come back to C2 and evaluate. We can choose x as a parameter for C1. It's kind of like independent, dependent, which one do you pick and move on. Once you see some examples, you'll get the idea which one should be the parameter in each case. I'm highlighting or circling the main parts that are new to you, so you could stay focused and keep those in mind. The equivalent or the equations for C1 become x is x. That's my variable, independent, that changes, and y will follow. That's how sometimes I say it. Y equals x to the second. So x is my parameter, where x changes from 0 to 1, as you could see. Now, the line integral along C1. Change everything to dx. That's my parameter. That's going to be dx dx. It's not going to go dx dt and dy dt. It's dx dx and dy dx, because my x is my parameter. That's a 1. And dy dx, you get it from here. And you change x. Well, actually, no, we don't change x, because x is my parameter. We keep it. Use u substitution right here. The derivative of u is 4x to the second becomes 8x. So you need an 8 here, you have a 2. Simplify it. I get u to the half becomes u to the power 3 over 2 times 2/3. And that was adjusted to 1/4. Do the math, plug in the numbers. That's the u substitution if you need more details. And that's my answer. So that was for C1. Let's go over C2. Over C2. This time I'm going to choose y as a parameter. For C2, we have y is my parameter, which changes from 1 to 2. And x is fixed to be 1. I know x does not follow, but you could tell that this would be a good way to start thinking about the limits for the integration. The integration will go from 1 to 2, and you're going to speak dy. That's the parameter language. Hopefully that helps. So I have 2x ds. That's my main integral. But now we're focused on the green, on C2. My parameter is dy, so I'm going to go dx dy, dy, which is 0. Sorry, this one is here, 1, and dx dy will be 0. 0 plus 1 square is 1, square root is just 1, and 2 times 1 is 2. dy, and y goes from 1 to 2, 1 to 2, as simple as that. And finally, we combine them to finish the problem. To finish the problem, we need to go over C1 and go over C2 and add them up, and that should do it. So parameter is a new language that you need to know which is the main part that takes you from to changes, and the rest will be taken care of as long as you do it right. If your y is your parameter, you're going to differentiate inside with respect to y with respect to y. Let's take another example. This one here says evaluate the line integral c of y squared dx plus x dy along C1 from -5, -3 to 0, 2, and along C2 from the same point A to the same point B. So you can see the same point. So the start point, the end point, either way are the same, but it's like a different path. Let's see what's the difference and write some notes. Part A, going with the green one. How do you parameterize this? I'll show you how, and everything like it will be the same concept. C1 will use vector notations, R of t to represent the move from this point to this point, and that's back a while ago when we studied how to represent lines and planes using vector calculus. So you go back to these sections, and I'll put them I'll put the links in the description below if you want to go back to these formulas. So here we go. R sub 0 points to this point, and R sub 1 points to this point. Doing the math, I'm going to put, instead of R sub 0, -5, -3 as a vector. And instead of R sub 1, I'm going to put 0, 2 as... I'm missing the t part, by the way here. There is a t part. So, using this derivative right here, and using this derivative right here, I got 0 and 2t. I have 1 minus t times -5. I have 1 minus t times -3. Add the components. For example, the first component, 0 plus -5 plus 5t, is just -5 plus 5t. The second component is -3 plus 3t plus 2t, which is -3 plus 5t. This is just basic steps. This gives me x of t, and this gives me y of t. And that's what I have, where t changes from 0 to 1. Now, while we are here, we could find dx dt, which is 5, dy dt, which is 5, or differently, I could say dx equals 5 dt, and dy equals 5 dt. Now let's go back to the integration and change everything to the language of t. the integration over C1, the green one, of this becomes the following. Replace y, replace x, as you can see. dx is 5 dt, dy is also 5 dt. Do the math. It becomes all like a polynomial with respect to t from 0 to 1, and I took the 5 out. Simple math, I have negative 5 over 6. Keep this number in mind because I'm gonna make a comment about this later on after we finish C2. So along C1, we came up with the line integral to be negative 5 over 6. Moving on. Evaluate the same line integral but going along the blue line or the blue path C2. In this case, we're going to choose y as a parameter, where y changes from negative 3 to 2. Now, why I picked on y, not x? Because x is a function of y, so it would be easier to use it that way instead of switching things and write y as a function of x using square root. So we kept it this way. Y is a parameter, and we keep it y as y. That's the parameter language. X will follow. Doesn't have to follow, but in this case it does follow, where y takes it from negative 3 to 2. Now if you find dx dy, it's minus 2y, or differently, dx equals. We're going to change dx because our focus is on the y as a parameter. Everything should speak y, and the integration should be with respect to y. Here we go. This will be replaced. This will be replaced. Instead of x, we're going to write 4 minus y squared. Instead of dx, we're going to write minus 2y dy. Everything is in terms of dy, one variable. Regular integration, polynomial. To the math, and I got 40 and 5 over 6. Here's notes and comments. Number 1. Notice that the line integral over the green one over C1 and the line integral over C2 did not give me the same answer, even though they have the same start point and the same end point. So make a comment about this. Even though the two curves had the same endpoints, we did not have the same answer. Thus, in general, the value of the line integral depends not just on the endpoints, also on the path, which way you're going, C1 or C2. Here's my comment too. In case you want to go, I'll call them A and B, from on C1 from A to B, and we call it C1. If you go from B to A along the same line, we call it minus C1. And that's going the other way around from 0, 2 to negative 5, negative 3, going from the top to the bottom side. And if you take your time to practice, you're going to end up with the following. X equals minus 5t, which is different than the first one, because my start is not the same start, and so on. You could double check. Let's say, for example, negative 5 is my end x component, and at the end t equals 1. Plug in 1 here. That's minus 5 times 1, which is minus 5, as you could see. Just to support why these are like this, different than the first ones. Now, if you do the math, going from B to A, if I call it B and A, we differently write it down as minus C1, and you're going to end up with positive 5 over 6. Earlier, I mentioned to you to remember that number. That number was -5/6. So this one will be the opposite. Or if you know that, you could just do it differently or quickly without doing all the calculations, and keep that in mind. Okay? Let's take another line integral. This example, I covered it in Green's theorem section. So we did this problem differently and quickly. Since the region R is closed and the curve is going around counterclockwise, we used Green's theorem. So we changed the line integral to double integral over the region R, and we finished from there and we get the same answer. But here's under line integral. We're going to go over C1, then C2, then C3. I will go a little bit fast because I want to save you some time from reading all the calculations, but you could slow down and pause the video, hitting the space bar. Look at the notes, see if it adds up, if it makes sense, then hit the space bar again to move on. Here we go. Using the line integral. So we're going to go over C1, C2, and C3. Green, blue, and red. For the green one, we're going to use x as parameter. X equals x and dx equals dx. So we have, when x equals x on C1, dx equals dx. It does not change. We don't say 1. It's a parameter. So instead of using dx and dy, we're going to change it to one variable, which is going to be dx. Y is 0, so delta y or dy is 0. So we end up with the following: x4 dx plus xy dy. Y is 0, this whole thing is cancelled, and that's what I have. From 0 to 1, because that's my parameter. Alright? So knowing that x goes from 2, that's kind of like another hint to see which one is the parameter. And doing the math, I have 1/5. Let's go over C2. Well, how do I go over C2? First, it's going from 1 on the x to 1 on the y. That's kind of like a slope of -1 with a y-intercept of 1. So you gotta find its equation, which is y equals 1 minus x. And I could use x as a parameter, my variable that changes, and y will follow. So x goes from 1 to 0, from 1 back all the way to the y-axis, which is 0. So I'm going to change everything to x. Dx, dx, everything will be dx. Dy has to change. Dy will be native, dx, right there. Instead of y, we're going to write y minus x. You could see that right there. Keep x, because that's my parameter. Keep x and dx, that's my parameter. Do the math, I end up with -1/30. C3. Y changes from 1 to 0. That's my parameter, dy. Y equals y. Keep it as is. X is 0. X cancels. That's going to cancel this. X cancels. The whole thing is 0, so I don't have to worry. The final answer is 0. Now we add them up, and the final answer is 1/6. Using Green's theorem saves you a lot of work, which is not part of this section, but I will leave the link below. And that should do it. Now, line integrals in space. C is a smooth space curve given by the parametric equations x equals x of t, y equals y of t, and z equals z of t from A to B. Or by the vector equations. As a vector equation, we're going to use I, j, and k. If f is a function of 3 variables that is continuous, on the same region containing C, then we define the line integral of f along C as follows. This is the line integral of f along C, and this is the detailed formula. This is ds right here. And this is f of x of t and y of t and z of t from a to b. That refers to delta t, of course. Differently, this is f of r of t, because that's r of t. And this is actually the magnitude of r prime. Those forms are basic forms that you need them from this section and on all the way till the end of the course. In case f is 1, we call it the length, not line integral. The length of the arc or the curve C from A to B if f is 1. There's no need to write 1 here. It's just like the integration of ds, which is the integration of this right here. And that should do it. It's about 27 minutes. And I have another one coming after this. Thank you for watching, and I'll see you in the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.